The F-106 is designed to be a fully capable, highly effective, all-weather interceptor for use by the United States Air Force Air Defense Command units. Deliveries to these units will start in 1959. The tactical versions of the Convair F-106A single place and the F-106B dual place are supersonic Mach 2 aircraft powered by the Pratt & Whitney J-75 P-17 engine. Both carry their armament internally, with basic armament for each consisting of 4 Falcon missiles and 1 MB-1 nuclear rocket. Test activities for the year 1958 involved detailed testing of all elements of the weapons system, from laboratory testing of components to an extensive flight program. The F-106A and B Accelerated Development Program involved 42 aircraft, of which 17 were assigned to the contractor portion of the test program. This film report will present the significant highlights of the 1958 program. For the purpose of this report, the program will be divided into 3 sections. The first, or flight test section, will concern those activities covered in the actual flight program. The second, or support testing phase, will involve those component activities investigated through laboratory-controlled examinations. And the final armament section will report on the development program designed to demonstrate F-106 armament delivery capability. At the Air Force Flight Test Center, in-flight examinations included evaluations of the F-106 external wing tanks, F-106A spin testing, J-75 engine evaluations, and the initial flight and preliminary flight test evaluations of the F-106B aircraft. Early in the year, aircraft 56-451 was assigned to the spin program. This program was conducted to determine the stall and spin characteristics for F-106A aircraft. Aircraft 451 received all special spin equipment installations at Convair San Diego Experimental Facility before being returned to Edwards Flight Test Center for the flight program. Recovery strakes installed on each side of the aircraft could be extended during a spin to assist in spin recovery. A spin recovery chute was installed in a special container mounted at the base of the vertical fin. Used as a secondary safety precaution against spin conditions, this device was activated by ballistically firing a pilot chute into the airstream, pulling the recovery chute behind it. Special pilot safety equipment included a single-action ejection seat and a modified G-suit to protect the pilot against longitudinal G-loads in the event of high spin rates. All equipment was thoroughly tested in flight examinations to ensure proper performance before beginning the spin investigations. A total of 31 spins were made, beginning with preliminary spins in April of 1958. Initially, recovery was made before a fully developed spin was reached. Later spins were allowed to progress until the full spin was accomplished. During these developed spins, a condition was encountered where the airplane would gyrate after stalling. This condition came to be known as a post-stall gyration. Detailed examinations of this condition determined its cause, the warnings preceding it, and the proper recovery technique necessary. Analysis of the data obtained in the spin program demonstrated F-106A compliance with the applicable Air Force specifications. Following completion of the spin program, aircraft 56-451 was stripped of all special spin equipment, provisions were added to carry external fuel, and a program was conducted to clear all F-106A and B aircraft to carry and use the external drop tanks. At the completion of tank installations on the aircraft, ground shake tests were made, clearing the aircraft for flight flutter testing at the Air Force Flight Test Center. These tests were satisfactorily completed with full tank loads at altitudes of 5,000 and 15,000 feet. Speeds were at Mach 0.75, 0.85, and 0.95. During jettison testing, 9 tanks were expended, 7 single-tank jettisons, and 1 dual jettison. Altitudes were at 15,000 and 35,000 feet. The drops were accomplished at 2 different speeds, Mach 0.4 and 0.95. At the conclusion of the program, external fuel usage testing was completed on aircraft 452 up to a speed of Mach 0.95, with altitudes ranging to 40,000 feet in climb, dive, and level flight conditions. As a result of this program, sufficient data was obtained to clear all F-106A and B aircraft to carry and use external drop tanks. During the 1958 test program, several changes were made in the F-106 propulsion system to improve propulsion and aircraft performance. Thinning of the external inlet duct cowlings resulted in a satisfactory drag improvement. The slotted ramp replaced the earlier perforated ramp. This change increased pressure recovery due to improved bleeding of boundary air and resulted in a 3% increase in thrust. A flight program to determine optimum ramp scheduling for the new slotted ramp established ramp operational standards for all production aircraft. 5 tail cone configurations were evaluated in a program consisting of 22 flight missions. The original cone, shortened by 4.6 inches, resulted in an effective combination of drag thrust improvement. Improvements in ejector design led to the acceptance of the convergent divergent ejector with the resulting thrust increase of 8% at design speed over the basic engine configuration. The Pratt & Whitney J75 P-17 engine was accepted for all F-106 aircraft over the earlier P-1 and P-9 versions. This engine included all basic improvements made in the earlier models. Rotating of the first stage inlet guide vanes and thinning of the second stage inlet guide vanes increased the flow area and resulted in relieving of low-energy stalls. First stage turbine inlet guide vanes were changed to a new alloy with heat characteristics that allowed higher operating temperatures than alloys used in earlier models of the J75 engines. The results of the propulsion program have confirmed the compatibility of the F-106 airframe and the J75 P-17 engine. These improvements have raised installed engine thrust and temperature limits to design specification requirements. F-106 aircraft, in which all of the new modifications have been incorporated, have now flown at the design speed of Mach 2. The first F-106B aircraft, 57-2507, moved off the production line at Convair, San Diego, during the early part of 1958. The aircraft was then delivered by truck to the Air Force Flight Test Center, and after thorough ground checkout evaluations, made a successful first flight on April 10th. The F-106B is designed to be a fully capable two-place interceptor aircraft with a complete F-106 armament system. It will serve as a tactical aircraft and, in addition, be used to familiarize pilots with the F-106A weapons system. Similar in appearance to the F-106A, the F-106B has a longer and slightly raised canopy. Dimensions are equal to that of the A. Wingspan, 38 feet, 1 inch. Overall length, 70 feet, 8 inches. Height to the tip of the vertical stabilizer, 20 feet, 3 inches. The approximate takeoff gross weight with full internal fuel load is 34,751 pounds. As a result of the similarity between the A and the B, the 1958 B flight test program was primarily devoted to examination of the significant differences between the two aircraft. Preliminary results have demonstrated that the F-106B maintains the same excellent handling characteristics of the F-106A. Climb and acceleration performance is essentially the same, with general performance in other areas comparable to the F-106A. Thorough testing of the complex electronic cooling and air conditions systems of an F-106 aircraft would be impractical using normal flight test methods. Necessary instrumentation and time would be very costly to the development program. For these reasons, an electronic cooling test stand laboratory was built at the contractor's San Diego testing area. The test stand chamber will hold an entire F-106 fuselage and is capable of recreating both transient and steady state temperature and altitude conditions for the entire flight range of an F-106 aircraft. Temperature can be varied from minus 60 degrees to 220 degrees Fahrenheit. The test stand method produces the data and development information necessary in proving the F-106 electronic cooling system adequate to the great demands made on it in actual flight operation. Changes in the F-106 cooling system, when proved necessary by test stand investigation, are incorporated into production aircraft following retest approval. A brief flight program confirms test stand results. The data available from this testing would be impossible to obtain without the test stand facility. The resulting savings in cost and time have proved invaluable in the F-106 development program. The skin of the 9 fuel tanks dispersed throughout the wings and fuselage of the F-106 are designed to withstand thermal stress as well as stress due to internal tank pressure and flight loads. The contractor established the Point Loma Structures test site in conjunction with the Air Force to test the effectiveness of the machine-sculptured, Scotch-weld-bonded tank skins. The jig work, electrical, fuel, and hydraulic systems here are adequate to subject fuel tank test specimens to a full range of simulated flight conditions. The tests conducted were on 3 tanks: the forward wing tank, the wing transfer tank, and the fuselage tank. Each tank was placed in its own special jig to most accurately apply flight loading conditions. All internal and external flight load conditions encountered in the full range of operation of an F-106 were mechanically produced through whiffletree and hydraulic actuator arrangements. Both static and extensive cycling loads tests were conducted through varying temperature conditions ranging from sub-zero through ambient to hot. Reduction of the data recorded from thermocouples, strain gauges, and other instrumentation determined that the machine-sculptured integral Scotch-weld wing tanks met design requirements. For the purpose of developing a high-efficiency F-106 radome, a special research and design group was formed within the electronic section of Convair San Diego as early as September 1955. Primary mission of the group was the development of a high-efficiency radome for the F-106. The basic concern was to design a radome which would allow efficient passage of the radiated energy search beam, and to ensure that the radar waves would complete passage through the radome with as little distortion as possible. The ideal radome would be electrically transparent, causing no radiation distortion. Since this is impossible, the distortions of the best possible radome must be measured and compensated for. To back up the design predictions based on this theory, the radome laboratory tested many radome experimental shapes with their complete test facilities. Bore sight range, direct physical measurement, high temperature dielectrometer, free space interferometer, and other complex equipment were employed. From this background of research and testing, the Convair Radome Design Group has developed a radome shape and manufacturing technique which meets the demanding performance requirements of the F-106 fire control system. The technique has resulted in two major conclusions. One, it has reduced the insertion phase difference, or IPD variation, from 10 electrical degrees to 1. And two, it makes practical a method of reproduction with high physical standard from part to part. In addition, engineers can now predict electrical performance in terms of known radar properties and can maintain electrical variations within extremely narrow error tolerances. Matched to the gimbal of the MA-1, the radar antenna is individually bore-sighted to ensure accurate installation, and final checks are made before the delivery of the aircraft to the Air Force. With these newly developed design, development testing, and manufacturing methods, a very high degree of accuracy has been obtained in this vital component of the fire control system. With today's interceptor aircraft pressing farther and farther into the range of supersonic speeds, the need and urgency for developing a pilot ejection system that will function at subsonic, transonic, and supersonic speeds at minimum and maximum altitudes is vital. In view of this, the Industry Crew Escape Systems Committee was formed to coordinate a developmental approach to safe ejection from supersonic aircraft. First considerations included both an upward ejection system and a downward ejection system. The Air Force assigned Convair the responsibility of developing the needed upward ejection system for Century Series aircraft. In Convair's program, two types of seats were originally considered: the A, or skip flow generator type, and the B, or bobsled type. After initial evaluations, Convair, with the approval of the ICESC committee, concentrated its development efforts on the second, or B, seat design. The pilot is ejected on his back at a 90-degree launch attitude, a launch position especially desirable because G-loads tolerances for humans are greatest at this angle. Preliminary wind tunnel and slingshot testing of a 1/10th scale model led to a full-scale wind blast program at the Air Force Flight Test Center. These runs were used to indicate the wind blast forces on the seat and pilot. In all, there were 5 runs conducted at speeds of 627 to 858 knots. Both low and high altitude flight gear was examined for wind blast results. In all post-run examinations of this test series, the pilot and his personal equipment was found to be in near pre-run condition. The first full-scale aerodynamic testing of the B seat was accomplished on the ARDC Supersonic Missile and Rocket Track at Hurricane Mesa, Utah. 3 objectives were accomplished in this test series. 1, the full-scale seat-simulated ejection performance as planned. 2, the validity of the slingshot tests were verified by the flight attitude of the seat. And 3, the test confirmed the results of the previous wind blast tests on the pilot and personal equipment. It was established that the seat configuration had good yaw and pitch stability, but did have excessive roll. At this point, telescopic booms were added to control the roll. Following slingshot evaluations, further testing at Hurricane Mesa using the new booms resulted in near-perfect seat flight, with no pitch, no yaw, and with only a negligible roll. During 1958, testing of the complete B-seat ejection system was conducted on the sled run track at the Air Force Flight Test Center. Speed for this series ranged from 132 to 750 knots. Results of the program to date have demonstrated that the B seat, as developed, will provide a reliable upward escape system for today's supersonic aircraft pilots. To date, this is the only type seat that has been successfully ejected from a sled-simulated aircraft cockpit at supersonic airspeed and remained aerodynamically stable and maintained accelerations within human tolerance. The sled tests showed that the configurations were stable over a speed range extending from 132 to 750 knots. It is felt that the operating principles of the B seat may be extended to much higher speed while maintaining good low-level, low-speed performance. In 1959, the B seat will go into hardware production for installation in tactical F-106 Interceptor aircraft. Initial F-106 armament phases and test programs are conducted at the Missile Development Center at Holloman Air Force Base, New Mexico. The activities here have fallen into 2 general categories: those involving Convair armament subsystems testing and those involving a joint contractor Air Force effort to harmonize the overall system. The Convair aircraft, numbers 458 and 460, were engaged in MB-1 ejection and ballistic studies and Falcon missile launching evaluations. The MB-1 ejection and ballistics program comprised a series of tests to demonstrate the compatibility of the unguided nuclear warhead rocket and the ejection system of the F-106. Prior to any live firings from an aircraft, inert rockets were ejected under various flight conditions. These tests determined rocket separation characteristics, but indicated that at a high Q condition, the rockets had high nose-up characteristics. This was corrected by a baffle and a 2-inch shorter stroke for the aft gun. Live motored rocket tests were made next to obtain clearance of the F-106A flight envelope. To date, MB-1s have been ejected on this program at speeds from Mach 0.9 to Mach 2 and over an altitude range of 10,000 to over 50,000 feet. The MB-1 ejection launcher proved efficient and highly reliable through repeated firings. The AD program, or Armament and Aircraft Weapons Control System Development Program, is a joint effort among the Air Force, Convair, Hughes, and Douglas. Among the primary objectives of this program was the flight operation of the highly advanced fire control system, the MA-1, designed and built by Hughes Aircraft. This MA-1 system is composed of many subsystems, each in itself a complex system: search and tracking radar, digital computer, communications system, navigational aid components, landing system aids, automatic flight control systems to be activated when cleared, and the armament auxiliary equipment. The MB-1 manual firing phase was started in December of 1958. 3 successful firings were made at an altitude of 20,000 feet and at a speed of Mach 1.25 against manned targets. The AD program provided the necessary changes required to give proven capability to tactical type F-106s in manual mode MB-1 firings. The accomplishments of the F-106 all-weather supersonic interceptor in its armament and in all flight testing to date has lived up to every design prediction.